Respected faculty members, attendees of the 4th International Conference on Holistic Innovation in Additive Manufacturing, and my dear colleagues. My name is Amrish Singh. I am a research scholar in the Department of Mechanical Engineering at Indian Institute of Technology, Guwahati. I am currently working in the field of laser-based directed energy deposition under the mentorship of Dr. Sajan Kapil and Dr. Manas Das. Over the course of next few minutes, I would like to present to you a novel method of powder feedstock handling in directed energy deposition. Directed energy deposition, or DED, involves a focused heat source which is directed onto a substrate, thus creating a small melt pool into which feedstock is injected. This leads to a growth in the mass and the volume of the melt pool, which upon solidification provides a deposited track. Through synchronized motion between the deposition head and the substrate, complex geometries can be realized in a layer-by-layer fashion. The feedstock handling in DED accomplishes powder metering, powder conveyance, and powder delivery. In the first phase of powder metering, a specified amount of feedstock is extracted from the reservoir, which is then conveyed to the delivery nozzle. The primary task of the delivery nozzle is to generate a convergent stream of powder particles whose focal spot matches the location of the melt pool. Almost all commercial DED units accomplish powder metering, conveyance, and delivery through pneumatic means. Several variants of powder feed nozzles exist in the literature. An off-axis nozzle, which is shown in figure A, is generally used for the cladding of rotary components, whereas coaxial nozzles are used for part fabrication and repair. It is important to note that an off-axis nozzle is non-omnidirectional in nature. This implies that the dimensions of the deposited track will be sensitive to the travel or the deposition direction. In other words, for instance, if the travel direction of the laser beam is towards the source of the powder feed, the dimensions of the deposited track will be significantly different when compared with its travel direction away from it. Apart from off-axis nozzles, all other variants exhibit omnidirectional capabilities. As previously mentioned, almost all commercial DED units feature a pneumatic feedstock handling system. However, this method of employing inert gases to accomplish powder metering, conveyance, and delivery has following limitations. First, high particle velocity, which is often characteristic of a pneumatic feedstock handling system, leads to a deteriorated surface finish and a reduced catchment efficiency. Second, inert gases, which are used to deliver the powder particles into the melt pool, dissipates the heat away from the melt pool due to forced convective cooling. This leads to a higher power consumption. Third, it is often observed that with a pneumatic system, the deposited tracks have a high dilution at the center and lack of fusion at the edges. This leads to an improper aspect ratio of the deposited track. Fourth, some studies have also suggested that the conveyance gases occasionally get trapped into the melt pool, which leads to track porosity and a decline in the mechanical properties of the fabricated part. Fifth, and perhaps one of the major limitations of a pneumatic powder feedstock handling system, is its compatibility with lasers and lasers only. Electron beams cannot be used with pneumatic powder feedstock handling systems as they require a vacuum environment for materials processing. In order to alleviate the aforementioned limitations of a pneumatic powder feedstock handling system, the following method of a gravity-based feedstock handling unit is proposed. In this gravity-based design, the powder metering will be accomplished through an auger. The rotational speed and the dimensions of the auger will govern the amount of powder mass to be conveyed to the deposition nozzle. This metered powder enters the deposition nozzle through an inlet port marked 1, which is then directed towards the center of the rotating distributor, which is shown here. This rotating distributor uniformly scatters the powder particle across its periphery, which then fall between an annular gap created by an inner cone marked A and an outer cone marked B. These powder particles eventually exit the nozzle in a conical and a convergent fashion with a distinct focal point. The proposed design also features provisions for supply of shield gases, which can be used for deposition in a non-vacuum environment. Also, the design has provisions for multi-material feed, which can be used for the fabrication of functionally graded materials or FGMs. To effectively handle cohesive granular media, the proposed design of the powder delivery nozzle also features an ultrasonically vibrating outer cone. This prevents the powder particles from jamming or clogging the narrow passageways of the deposition nozzle. In order to establish the feasibility of the proposed design, discrete element method or DEM simulations were performed. Discrete element method or DEM, unlike CFD or finite element analysis, places emphasis on individual powder particles, which when assembled gives the macroscopic outlook. In other words, in discrete approach, the macroscopic behavior of a system results from the microscopic interaction amongst the constituent particles. This flowchart outlines a generic soft particle DEM algorithm. The simulation first starts by initializing the problem. Then, given the initial conditions, Newton's laws are used to compute the particle acceleration and subsequently its velocity and position. Having determined the position of particles, a contact detection algorithm is run, followed by computation of the contact forces using appropriate contact force model. These forces are then used to perform subsequent iterations. Hertz-Mendelian no-slip theory was employed as the contact force model for this study. The Hertz-Mendelian theory bifurcates the contact forces into its normal and a tangential component. These forces can be computed using the equations listed out in these two columns respectively. Also, a damping force is associated with each of these components. A damping force mimics the loss of energy during collision. The simulation results show the design's ability to generate a conical and a convergent powder stream. Also, the results highlight its effectiveness in uniformly mixing and dispensing multiple materials for use in fabrication of functionally graded materials. This figure shows the powder stream as it exits the nozzle and travels down in a convergent flow pattern. Planes marked as 11, 22, 33 up to 99 highlight the location of observation perpendicular to the nozzle axis and relative to the nozzle outlet. It is evident from these images that the powder stream remains convergent up to a length of 25 mm, beyond which the stream diverges. The performance metric of a rotating distributor is its ability to uniformly disperse the incoming powder mass along its periphery. This should be achieved without making any compromise to the mass flow rate. To quantify the uniformity of powder dispersion by the rotating distributor, following method was employed. Underneath the rotating distributor, 36 equally spaced virtual mass sensors were placed. These sensors are highlighted with a solid blue line. These sensors record the total powder mass at any given instant. By observing the percentage variation of average powder mass recorded by each of these sensors, spatial distribution of the powder particles can be quantified. Three simple designs, as illustrated here, were the subject of this analysis. For a straight blade distributor, the number of blades on the disc has very little effect on the spatial distribution of the powder particles unless the number of blades approach a very high value. However, this design was able to maintain a relatively high mass flow rate. For a curved blade distributor, as the number of blades on the disc increase, the percentage variation amongst the mass sensors fall. This signifies a better and a uniform spatial distribution of the powder particles across the periphery of the rotating distributor. However, this improved spatial distribution comes at the cost of mass flow rate. As the number of blades increase, the passageway for the powder particles on the disc becomes narrower. This decreases the mass flow rate and eventually, with sufficiently high number of blades, leads to clogging. Out of the several tested distributor designs, a two-stage distributor provided the best results. This design features two rows of blades rotating opposite to each other on a single disc. The recorded percentage variation amongst the mass sensors was 12.58%, while registering an average mass flow rate of 27 grams per minute. This improvement in the spatial distribution of the powder particles can be attributed to the observation that the first stage retains the powder particles for a short duration of time before delivering it to the second stage for further dispersion. Essentially, the first stage acts as a buffer, retaining the particles long enough to create a steady flow of granular media to be delivered to each of the blades of the second stage for further dispersion. Testing with initial prototypes of the proposed design qualitatively validates the DEM simulation results, which establishes product feasibility and identifies performance aspects which require further improvement. This work proposes a gravity-based feedstock handling system which can serve as a viable alternative to the conventional pneumatic design. Following are the few key conclusions from the study. First, powder flow under the effect of gravity in the proposed design is of conical and convergent nature. Second, a two-stage distributor is preferable for generating temporal and spatial uniformity in the powder stream. Third, experimental results presented in this study are qualitative in nature. Currently, efforts are being made to quantify these results. This will ascertain the focal length and the spot size of the powder stream. Fourth, certain aspects of the design are still undergoing improvement trials. Fifth, achieving a smaller focal spot diameter still remains a challenge and is part of the ongoing work. Thank you very much for your attention.